today about this sort of looks a little bit esoteric, but I guess with old age one can sort of indulge on things and see where do they lead. And I like this structure very much. So this is of course the work has been done on and off around the last 4 or 5 years with Alfredo, and owes a lot of his insights on chords and centers, and so this is sort of an I consider myself a student of his. So this is my what I think. What I like very much is that a nice structure under here, and it's good to bring it up. So, okay, this starts with the classical phase space, and you have 2 points in phase space, and you have chords and centers. No, wait. Oh. Okay. At point. How do you point? So you have a center, which is the center of a reflection, and the translation, which I use half translations because it makes formulas much simpler. These 2 operations in phase space satisfy a group, and this group will appear in 3 different contexts during the talk. So so this group is represented in quantum mechanics in very well-known. You have translation operators, you have reflections operators, which are a Fourier transform of them. And again, the group structure is reflected up to a phase, which is well known, and it leads to the non-commutativity of operators in quantum mechanics. So nothing new here. So these both translations and reflections constitute bases of operator bases with the scalar product defined by the Hilbert-Schmidt, and then you can use either translations or reflections as complementary bases in quantum mechanics, and with those you can represent operators in terms of their Wigner or their Weil, and I will sort of try to insist that both are, it's essentially like using coordinate representation or momentum representation in ordinary quantum mechanics. And in fact, both are related by a Fourier transform. If you, this is, if the phase space is flat, that's what I just said. Now, if you put periodic boundary conditions, both on positions and momenta, then the phase plane becomes a torus. And there are some well-known consequences in quantum mechanics. The momenta become discretized, positions also become discretized, and what is also is that H bar only can take inverse integer values. So the Hilbert space for this this problem is finite. It's of the Hilbert space is of dimension d, and then operators will be matrices in d by d matrices finite. So so that's all there is. It's very well known. Now, if you want to go to label translations and reflections, and this is the first thing. Now, both will be labeled by half integers. So while positions and momenta are labeled by integers, reflections and translations in a discrete phase space are labeled by half integers. So you need double the dimension of the arrays. So if you label now the translation and reflection operators by integers, you end up with exactly the same structure. Now the coordinates for the reflections and translations are I will use integers, and then they belong to a periodic array of 2 by 2, 2D by 2D, and that's the phase space that that one needs to use. Of course, these translations and reflections are now periodic in a 2D lattice, but they also have a shorter quasi-periodicity, so they are periodic up to a sign, so that they are really redundant bases as operator base. And this is what it is. You now have the representations of operators or states are now discrete, periodic 2D by 2D arrays, which are the Wigner or the characteristic function if A is a quantum state. No? So these are, again, they are complementary. There is this problem of overcompleteness, because as operator bases, you need only d square and not 4d square, but this is very easily taken into account by a simple change of the normalization. So this is a wave packet is represented in the center or in the chord representation. You have here, this is the packet which has a certain coordinates, but then this interferes with the image on the torus, so it gives this characteristic pattern of oscillation between two distant classical objects. And the same happens in momenta, and so this is a pattern that will repeat. In the chord representation, on the other hand, where is the here? Because this is a wave packet, it only has very small chords. Chords are centered on a very small region, and of course there is also this reflection on the torus, and the position of the state is reflected by phases inside that by the phases of those chords that are always small. So now let me go to superoperators. So we want to use these two operator bases as descriptions of superoperators. That means linear transformations on the space of operators. So, and in this case, you have two different possibilities. Oh, no. You see, when you have an operator basis, you can have the standard, what we call the standard linear action, in which you treat the operator basis just as the ordinary bras and kets in quantum mechanics. So the action of this bracket superoperator on an operator is just the scalar product of this one, just like the standard action on a wave function. But there is a different possibility in which the same two operators could act just by fitting the operator in between the two. So, and this we call the Choi conjugate action, for reasons that will come recently. So when you expand a superoperator in terms of these bases, you can expand it in the usual bracket form, and then you get some coefficients for the expansion of this superoperator. But you can also expand it in a different basis, like in this, and we call this the Choi conjugation between these two. The name comes from the fact that in quantum information there is an operation in which there is something called the Choi-Yamiolkowski isomorphism, and it goes from one basis to the other when the bases are computational basis. That means transition basis. Now, what I want to emphasize here is that there is a general way. Here. There is a general way of going from one description of the superoperator to the other, and that requires computing a trace of 4 basis elements like this. And that allows me to go from one basis to one description to the other. If you take transition basis, then to go from one to the other, you just have to interchange 2 indices. That's how it's done in the theory of quantum channels. It's very common to do that. But what we want to show here is that if you use phase space based bases like the transition and reflection operator bases, then that transition from one to the other enacts something like a Wigner transformation from one basis to the other, and that's what I want to show. So it's sort of you can compute easily this. This is a superoperator. You see, it's reflected. Wait, I want to say one more thing here. In the when you describe a superoperator in this way, it's sort of easy to see what the properties are as a quantum channel. So, for example, if this matrix is positive definite, then you diagonalize it and you immediately get to the Krauss representation of a superoperator. On the other hand, this other basis as matrix elements allows you to find the spectral properties of the superoperators, like iteration problems, like time evolution, and spectral properties of. So the two are. It's nice to have them both, like and that's what the Choi-Jamolkovsky isomorphism exploits. You write down a superoperator in that in this way, in this way, and then you find the spectra in the other way. So that's and what I want to stress now is that this transformation, when you look at it in a phase-space basis, like of translation or reflections, you get like a Wigner function for superoperators. So I will define, you see here I have defined a translation operator. It has two indices, one that comes from reflections and another that comes from translation. So it is a superoperator which has four indices. It's defined in this way in one of the two systems and in this way in the other. Analogously, you can define a reflection superoperator in this way, and it turns out that they have exactly the same group structure of the Heisenberg group file, and so that you see you can define a symplectic product in terms of this, and then you have that the translations are they are unitary, and they satisfy this property. Then the reflections are also Hermitian, besides being unitary. They square to 1, and they are periodic in the so they have exactly the same property, group property of the single structure, but now it's a superoperator structure. So you have exactly in Hilbert-Schmidt operator space, what you have is exactly the same idea, that you have reflections and translations which are related by a symplectic transformation, and then it follows that you can define so you take the trace of the superoperator with reflections, and you get kind of a Wigner function, which has all the properties of a Wigner function. Or here, you take it with the translation operators, and you have all the properties of a characteristic function. So this is this is like a double phase space in which you have translations and reflections and Wigner functions and non-Wigner and everything. Eh? You tell me how much? Okay. Okay, so you see, now you can represent a superoperator as a combination of super reflections or of super translations, and these are so you see, when you do it this way, it is represented the way a Wigner function is expanded. So you have a Wigner function, you take the reflections, and then you get the operator, and you can, if you want, get the matrix elements of this superoperator. So it works out in exactly the same way that that you have for Wigner and characteristic functions. So here, for example, the trace of the superoperator is given by the characteristic function at 0. That's the chord function at 0 is the trace of the superoperator. It's also an average over the center function, the Wigner function, just like you have that the trace of the product of two superoperators is given by the product of the Wigner representations. So everything works exactly as in the single phase space, except now one is in double phase space. So let me see one way that one can. It's well known that if you take a phase space function, a classical phase space function, the way to generate an operator from it is just to multiply it by reflection. So this is called the symmetric quantization of a classical operator. No? Now, if you do the same here, if you take this superoperator, turns out to be diagonal in the reflection basis. Now, because this is a function only of x, which are the coordinates. If you take a function of momenta, which are the chords, then you get an operator which is diagonal in the complementary basis. So this would be like, if you have a sum of this plus this, what you get is like the of p squared plus q squared. No, but this works exactly in the same way. So now I'm going into some examples. You have a superoperator which is unitary evolution. This is so if you want to evolve either a density matrix or an operator, you just plug it in there. No? So this is if you want the simplest superoperator. If you wanted matrix elements in the reflection basis, this is the kernel, no, that propagates the Wigner function. And now, if you go to the other representation, then this superoperator is just the trace of with the super reflections, and it turns out that in this simple case, it's just a product of two Wigner propagators, which is just the Wigner function of the unitary unitary map. And so here you have this. Here you have the spectral properties of this operator. Here you have the propagators of the unitary map. And this is the basis for further. Each of these will be, in the semi-classical regime, will be the exponential of a generating function. And then if you evaluate that sum or integral by stationary phase, you get semi-classical approximations to the super propagator. There's another area where this is useful. If you use the same techniques as before with the density operator for a pure state, then it turns out you can find a host of relationships between Wigner functions and characteristic functions of pure states. So, like for example, I don't know, this you have this is it's particularly nice, I find, because you have this is like an inverse participation ratio in phase space, which gives the it can be computed either from the Wigner or from the characteristic function. It gives the same result for pure states. And it turns out in the discrete, in the continuum, I don't know, but in the discrete part, this is what characterizes symmetrically, informationally complete basis in quantum information. So this quantity has an upper bound, which is very simple, but it also has a lower bound in the discrete case. And that is quite important because that lower bound is the tool that one uses to compute this SIC, symmetric informationally complete. Well, it's a long, but this is quite useful in quantum information. There is another quantity which is very interesting. It is the Wigner. These are all positive quantities. It's the Wigner function computed at x and minus x, and that's the same as the fourth power of this complex value, which is the characteristic function. You can also have expressions for Wigner function of transitions between pure states. This I wrote down in the discrete case, but equivalent, you just replace the sum by an integral and are available in the continuum. In that case, with Alfredo, we were able to write down a huge number of previously unknown relationships between Airy functions and other special functions. Because you see, if you have the Wigner function, for example, for linear Hamiltonians, leads to special functions like Airy or okay. So let's. So this is another application of these techniques is, so here I write down a quantum channel. It is clearly written directly in Krauss form if these coefficients are positive. And you see what it does. If this is a narrow Gaussian, this is just a coarse graining channel in phase space. So you take a density matrix, we shake it a little bit with some coefficients, and you get coarse-grained dynamics. We have studied this for a long. This is this operator. When you compose it with a unitary operator, it's not anymore normal. So it has a spectral decomposition like this, and these coefficients lead to usually to decays, which can be this we have studied this composition of the unitary map with the diffusion kernel, and the spectrum of this is usually inside the unit circle, and it has a leading eigenvalue, which leads to the Ruel-Polycott resonances of this map. I'll come back to this So let me now go to an application to all these things together. You know, the talk, it's out of time order correlator, is defined as the norm of the commutator of two operators at different times. So if you look at it as an average, it has 4 time insertions, all at the same time. That's the origin of the name. No? And the question is that it has been recently used as a way of discovering quantum chaos in various systems, including very complicated systems like black holes, and it has been used very recently by Maldacena as a way to characterize chaos in quantum mechanics. Now, what I want to show is that the translation basis is the ideal tool to look into this and how to understand why it should reflect in quantum mechanics the chaotic, the classical chaotic features of the evolution. So if you use the unitary if you if you use the unitary evolution, this is the what we did before. This is the translation basis unitary propagator. You get the matrix, you compute this, and you end up with this formula, which is quite general. There's no, so what you need to know is the matrix elements of the superoperator in the translation basis, and you get multiplied by this sine square of the symplectic product of these two things. So, so the sum involves probabilities. The probability that if you start with the chord psi, you end up with the chord alpha. Semi-classically, this is the way you compute you compute the Lyapunov exponent. You start with a chord, small chord, you propagate the two tips, and you measure the end of the chord. And that gives the Lyapunov. So now, if for short times, if you take a small chord and you propagate it, what this probability distribution will be strongly peaked at the classical chord, no, at the chord propagated classically. So it's clear that this, in the for short times, this will just be a result and that shows precisely the exponential growth. Maybe a picture will show. You see, this is how classically you compute the Lyapunov exponent. You start with a small chord, you propagate the two tips, and you end up with a larger chord, which for short times will be exponentially times this. So the commutator measures this area. So this area will have a short side and a very long side, which is a measure of the length of the chord. No? So this is how you end up with the growth of the Lyapunov exponent for short times. Now, for longer times, then you use the coarse graining argument, and you add just a little bit of noise, and the superoperator then at longer times decays with the first Ruel-Polycott resonance. So what you get is that I think this should be better explained, but I am running out of time. But so you know, if you combine the diffusion channel with the unitary channel, you end up that in the short time limit you have an exponential growth depending on the Lyapunov exponent. And for longer times, what you get is the decay ruled by the first Ruel resonance. So here is the model we present. So you see, here we use Hermitian operators made up with very small, I mean, to measure the Lyapunov, you have to start with a very small chord. You cannot start with a long chord, because you're not. So this is the shortest chords available in a discrete phase space. And so you take this operator, then you compute. You compute with the Arnold scat map. Then you get the evolution is linear, and then when for the unperturbed cat map, you get exactly this sine square involves one element of the monodromy matrix, which of course grows exponentially, and then you get this up to the log time, of course. When the chord has reached the edges of the torus, then it starts wrapping around, and then you get many chords for the final thing, and you get something that is saturates at a constant value. Okay, so these are the numerical results. So you see this is the correlator. It grows. This is the Lyapunov exponent. This is the Rouel resonance. And what you get is first the growth and then the decay. This is the without any 30. No, 33. I have okay. No. So so you see in the full unitary case, which is this white dots, what you get is this coefficient grows and saturates. And the interest is to see if the approach to saturation has anything to do with the decay of correlations. For that, you have to subtract the constant value, and this is done here. So you see here that if you subtract the constant value, this in the beginning you don't see the Lyapunov, and then you get to see a decay, which as you add a little bit of noise, it becomes very soon the classical Rouel resonance decay. So in conclusion, you see this correlator is able to reflect the two interesting chaotic characteristics of a map, which is on one hand the exponential increase of distances in phase space, and on the other hand the decay of correlations, which are also a characteristic of chaotic motion. This I can skip. So, conclusions. I think the one message is that there are phase space techniques available to describe superoperators. If somebody is willing to use them, that's it goes on their own. So the double center and the double chord distributions implement this Choi isomorphism in special bases on translations and reflections. There are many quadratic and quartic relationships that come from this manipulation. And finally, I think the chord-chord representation allows a quite complete description of the Autok time dependence.